In this video, we are going to look at electric field intensity. So first thing is we can define what electric field is. Suppose you have a charge here placed at any point. So this charge, let's call it Q, all around it, this charge will create its influence. So what it means is that if you bring another charge here, you will see that that charge will be affected. This new charge placed here will feel that there is something pushing it away. This new charge Q here will experience that there is another charge Q there. Yeah. So what is happening is that this charge Q is modifying the space around it so that any other charge will experience some force. And this influence that is being created by this charge Q is known as the electric field created by this charge Q. Let me put this in words. The charge Q will create some influence in space around it, such that any other charge in this space will experience force. In other words, I mean, this is important that we write this. In other words, Q will modify the space around it in some way, and we say that charge Q has created electric field around it. Now, how strong is this influence? How strong is this electric field around this charge? Is called the electric field intensity. So electric field intensity gives us a measure of how strong the effect is in this space. We can use Coulombs law straight away to find the electric field intensity. So I will straight away give the formula here. So suppose I go back to this situation. Suppose there is a charge Q here, and this is my point where I want to find the electric field intensity, and this distance is d from here to here. Then the electric field, let me write it, the electric field intensity at point P which is at a distance of d from charge Q, and here I should clarify that Q is a point charge. From point charge Q is given by this formula, KQ divided by d square, and you should be able to compare this formula with the formula for gravitational acceleration. If you recall, gravitational acceleration A was gm over r square. So these two formulas look quite similar. Now just E is a vector quantity. Electric field intensity E is a vector quantity, which means that it has its direction as well. And the direction is, I can say here that the direction of E is always away from a positive charge and always towards a negative charge. Now let's look at some examples now. So very simple example is straight away this. Here I got a 18 microcoulomb charge. This is my Q basically, and this is my point P where I want to find the electric field intensity, and the distance between them is 6 meters. So I want to find electric field intensity at P. So I can say the find electric field intensity E at point P. We already know the formula. So formula is E is equals to KQ over D square. So K is 9 times 10 to the power 9. Q is 18 times 10 to the minus 6 microcoulomb, and 6 square is this, and that gives me a value of 4,500 Newton per coulomb. And we can give the direction as well. Here it will be I can say towards right, because my Q is positive, this Q is positively charged, so electric field will be away from it. So electric field at point P will be towards the right in. So I can say towards right in above diagonal. Simple example. And example number 2, here we will look at two electric field because of two charges, and then we will do vector addition. Just to again remind, E is a vector quantity. So if we are trying to find net electric field because of two or more charges, we need to do vector addition. So this is my next example here. I got 4 microcoulomb here. Let me call this Q1. Another charge is 3 microcoulomb. Let me call that Q2. They are separated by a distance of 5 meters, and I'm interested in finding electric field intensity at point P between them. So what we are doing is find E at point P. So here at P we will have electric field intensity because of Q1, and we will have electric field intensity because of Q2, and we will need to add them vectorially. So this is my point P. First let's consider electric field intensity at P because of Q1. Now Q1 is a positive charge, 4 microcoulomb. So at P, the electric field intensity because of this 4 microcoulomb charge Q1 will be away from Q1. So that's my electric field intensity because of Q1. I can calculate this. E1 is equals to K Q, and I'm talking about Q1 here, so K Q1 D square, 9 times 10 to the power 9, that's my K. Q1 is 4 times 10 to the power minus 6, and then D square is 2 square, and that will give me a value of 9,000 Newton per coulomb. So this E1 is equals to 9,000 Newton per Coulomb. Okay, so likewise, now we look at the electric field at P because of charge Q2. Now Q2 is also positively Q2 also is positive charge. Therefore, the electric field because of Q2 will be away from Q2, which means at P the electric field because of Q2 will be like this, away from Q2, and we can plug in the values there. KQ divided by D square, K is same, and Q this time is, we are talking about Q2, so 3 times 10 to the power 3 times 10 to the minus 6, and D is 3 meters here now this time, so 3 square. That gives me a value of 3000 Newton coulombs. So this is my 3000 Newton per Coulomb. Net electrical intensity, we just need to do a vector addition, and we can clearly see that net E is equals to, I mean, the right hand side is bigger. I haven't drawn them proportionately, but that's okay. The electric field towards the right is 9,000, towards the left 3,000, so net will be towards the right. So net will be 9,000 minus 3,000 is equals to 6,000 Newton Coulomb towards the right. Towards, you can say towards Q2, or towards, I mean, you can also say towards, you can say simply towards Q2, or you can say towards right in above diagram. That's my Q2, and we can look at one more example, which is again would involve some vector addition. So this is my, this time I got this coordinates of this point are 0, 4, and charge I have is microcoulomb, and I'll call that Q1. Another charge that I have here is 9 microcoulomb, and this is 3 meter, and all I'm trying to do is, this is my origin, or call it point P. Find electric field intensity at the origin, which is, I can say, call origin is normally always O, so I don't want to use P there. So at origin, so we do the same thing just like previous example. So here we got Q2, and this is my origin here, this is my point P or origin, and I'm going to find electric field intensity at this point because of Q1 and because of Q2, and then I'm going to vectorially add them together. So let's look at electric field at point O at the origin because of this 6 microcoulomb charge. Now 6 microcoulomb is a positive charge. Electric field will be away from the positive charge, so it will be away from this positive charge. So here it will be at O, that will be the electric field intensity because of Q1. We can calculate the value of E1. E1 is E at O because of Q1, and formula is simple, K times Q divided by D square. So K is same, 9 times 10 to the 9. Q is my 6 microcoulomb divided by D is 4, so that's 4 square, and that gives me electric field intensity of 3375 Newton per Coulomb. So this is 3375 Newton Coulomb. Now let's consider the charge Q2. Because of charge Q2, we have electric field intensity at O. Now charge Q2 is negative, which means that electric field intensity will be towards the negative charge, which means at O the electric field intensity will be like this. Let's call it E2. So E2 is we are talking about Q2 now here. So I'll just just use the formula KQ divided by D square. So KQ is 9 times 10 to the power 9. Again, remember, we just need to use the magnitude of the charge here, because positive or negative only will give you the direction. So KQ divided by D square, which is 3 square, and that gives me electric field intensity of 9,000 Newton per Coulomb. So far so good. Now these are vectors, so I have to do a vector addition. So vector addition, we just know how to do that. When we need to draw one vector first, and then we need to draw another one. So E2 is 9,000 here. So that's the first vector I'm drawing. This is 9,000, and from the tip of the first vector I draw the second vector. This is 3375. Familiar steps, I think, for all of you now. And this angle theta we'll need to find. So this is my net electric field intensity, which is equals to, just using Pythagoras theorem, 9,000 square plus 3375 square, and that will give us 9612 Newton per Coulomb. And the theta I can find as tan inverse 3375 over 9,000, and that will be 20.56 degrees. So net E is equals to 9612 Newton per Coulomb, and I can see this is the negative x direction, so I can say 20.56 degrees counterclockwise from negative x axis.